Hello everyone. Welcome to part 5 in our series on solving differential equations using Laplace transforms. Today we're going to be talking about shifted transforms. Okay, we want to do the Laplace transform of this. This is e to the ct, where c is any number, times f of t, where f is a function that we do know the transform of. Okay. How do we figure out what this is? As usual, we use the definition of Laplace transforms. Improper integral, 0 to infinity, e to the ct, f of t, e to the minus st, dt. That's the definition of the Laplace transform of this compound function. Okay, I can combine those two exponential terms. So I get f of t e to the minus s minus c times t dt. Okay, if we look at this integral, we realize this is the same as the Laplace transform of f, except that instead of s being right here, we have s minus c. Well, s and c are constants in this integral, therefore this integral equals capital F of s minus c. Here, capital F is the transform of little f. The only thing that's different, instead of having f of s here, we have f of s minus c. And graphically, if you were to graph f of s and then graph of f of s minus c, you would get the same graph except that this would be shifted c units to the right compared to the original graph of f. So that's why we call this a shifted transform. If we know the transform of little f, then we know right away how to do the transform of e to the ct times little f. It's just our original transform evaluated at s minus c instead of evaluated at s. Okay, let's see how we use this new formula. I've put that formula here in red. It's another one of these things that we're just going to add to our library of Laplace transform properties. Let's apply this to figure out what the Laplace transform of this is. This is a function we didn't know how to transform before. Now we do. I look at this and I go, okay, here's my function f of t. My exponential e to the 2t, looking over here, means that c is equal to 2. That's going to be our shift. It's going to be a right shift 2 units. We do have to know what the transform of little f is, otherwise this formula over here really doesn't help us a whole lot. But we do. The transform of t is 1 over s squared. Therefore, the Laplace transform of t e to the 2t equals this function shifted to the right by 2 units. That's just 1 over s minus 2 quantity squared. That's it. Knowing this original transform was essentially all we needed to know to get the transform of this compound function. Just shifts this transform 2 units to the right. Okay, let's try another one. E to the minus t cosine of t. Okay, don't be fooled by the fact that I wrote e to the minus t first. Here's our f of t, and I see e to the minus t. That means that c is equal to minus 1. We're still going to use this identity, except instead of s minus a number, we're going to have s plus a number. We're actually going to have capital F of s plus 1 in this case. We do need to know what capital F is. And if you remember from a previous video, the transform of cosine of t is s over s squared plus 1. Okay, putting all that together, the transform of e to the minus t cosine of t equals, I basically take my transform here and replace every instance of s with s minus c, which in this case is s plus 1. So I get s plus 1 over quantity s plus 1 squared plus 1. That's it. This is the transform of our compound function, e to the minus t cosine t. Okay, let's use this to solve a differential equation. I mean, after all, that's what we've been using Laplace transforms for. Here we go. I've already written it here. I'm taking the second derivative of y plus 2y dot plus y equals 3t e to the minus t. Here's two initial conditions. These dots, if you haven't seen them before, that's just shorthand for the time derivative. So this is the second time derivative. This is a single time derivative. It's just a nice shorthand. Okay. As usual, we start by taking the Laplace transform of both sides. So Laplace transform of the second derivative, that's s squared capital Y minus sy of 0 minus y dot of 0. That's the Laplace transform of this term. The Laplace transform of this term is 2 times s times capital Y minus y of 0. And then finally, the Laplace transform of this is just capital Y. That whole thing is going to equal the Laplace transform of this side. Well, now we can apply this formula. We already know the Laplace transform of t. It's 1 over s squared. And this is going to shift that to the left. Instead of s, we're going to get s plus 1 because c is minus 1. So I get 3 times 1 over quantity s plus 1 squared. All right, let's simplify things a bit. As usual, we collect terms with y, with capital Y. And I get s squared plus 2s plus 1. That's this term, and this term. I can fill in my values for y of 0 and y dot of 0. So I get minus 4s minus 2 minus 8. I think I did that right. Right, we had minus 2, and then I had plus 2 times minus y0. That's a minus 8. Looks like we got it. And that's equal to 3 over s plus 1 quantity squared. All right. Remember, our goal is to solve for y here. Y times s plus 1 quantity squared, that's what this is. I'm going to put everything else on the right-hand side, so I get 4s plus 10 plus 3 over quantity s plus 1 squared. Let's divide through by s plus 1 quantity squared, and I get 4s over s plus 1 squared plus 10 over s plus 1 squared plus 3 over s plus 1 to the fourth. There we go. That's the expression for the transform of our solution. We now have to go backwards to figure out what the actual solution is, what little y is. And we're going to take each of these terms individually. Okay. Now, I notice that everything has an s plus 1. That should remind us or let us know that we're dealing with an e to the minus t in our original function. Because you remember, that shifts the transform to be s plus 1 instead of s. So each of these terms is actually going to have an e to the minus t in it. Just a few notes. Remember that t transforms as 1 over s squared. T cubed transforms as 3 factorial, which is 6 over s to the fourth. That looks like these two terms right there. This term I'm not so sure because we have an s over an s plus 1 squared. That's a little weird. So the way we handle this kind of thing, if I already see that I have a shifted transform, I need every s to be shifted in the same way. Well, what do? I actually make that shift happen up here. Let's see how we do that. Whoops. Wrong color. Can't have that. Okay. Now you're going to think this is a little weird, but I'm going to add 4 and subtract 4. I can do that because I'm really just adding 0. So I haven't changed this expression from here because I've just added 0. Okay, why have I done that? 4s plus 4 is the same as 4 times quantity. Erase that, replace that with 4 times quantity s plus 1. That's what I wanted. I wanted to make sure that if I have an s plus 1 down here, I also have an s plus 1 up here. These other two terms are fine as they are. I don't really have to do anything with those. Although I am going to do something interesting here. Remember that the transform of t cubed has a 6 in the numerator. I don't have a 6. What I can do, kind of like what I did here, I can make the 6 happen. If I multiply the 3 by 2 and turn it into a 6, I just have to make sure I divide by 2. So here I'm making sure that the term stays the same. 1/2 times 6 is 3. The reason I need the 6 is because I want to match it to this transform. Okay, we're almost done. We've done the hard stuff. I'm going to take these two terms and split them. So I get, here I'm going to get s plus 1 over s plus 1 squared. Well, that's 4 times 1 over s plus 1. I get minus 4 over s plus 1 squared plus 10 over s plus 1 squared. That's 6 over s plus 1 squared. And then finally I have 1/2 times 6 over s plus 1 to the 4th. Okay, I think we're in good shape. We're ready to actually invert the transform. Y of t. Now we're looking at the solution. What function has a transform of 1 over s plus 1? If you remember your little table we've made in previous videos, that's just e to the minus t. Plus, what function has a transform of 1 over s plus 1 squared? Well, that's like 1 over s squared. That means we have a t, but it's going to be shifted with an e to the minus t. Finally, we have 1/2. This is a shifted version of the transform of t cubed. So we have a t cubed, and we still have an e to the minus t. We're done. We did it. I suppose if we want to make this look a little bit nicer, we can factor out an e to the minus t. And I get 4 plus 6t plus 1/2 t cubed. That's the answer. Might as well put a nice box around it. So we used our shifted transform formula to allow us to solve more complicated differential equations. Well, that's it for this video. I hope you enjoyed it, and I'll see you next time.